We are already on. Hold on just a second until it goes up on the YouTube as well. We are already on. Okay, there we are. Okay, thank you very much, everyone. We are starting again our session of the ANTECIPA National Meeting, Congress, and I leave the word to Thiago Pugliere, who is our host of this session.
Good afternoon. Welcome back to the conference and to the Roundtable Conservation of Modern and Contemporary Art with a group of scientists from the Getty Conservation Institute. It's a pleasure to receive Tom Lerner, a senior scientist and the head of the science department at the Getty, Odile Madden, a senior scientist leading the Modern and Contemporary Art Research Initiative, and Ana Lagana, a research specialist in the conservation of plastics, also within the Modern and Contemporary Art Initiative. Tom is both a chemist and a conservator with a PhD in chemistry and a diploma in conservation of easel paintings. Odile has a PhD in material science and engineering, a master in history of art and archaeology, and an advanced certificate in the conservation of historic and artistic works. And Ana has a diploma in conservation with a thesis on plastics, also working with chemical and physical analysis. I would like to thank Tom, Odile, and Ana for kindly accepting this invitation and sharing your knowledge and experience with us. Now we will have your presentations of 25 minutes each, followed by 15 more minutes for discussions. I just remember that the participants can make questions in Portuguese or in English at any time in the chat, and we will consider them at the end of the presentations. Please, Tom, the screen is yours.
Thank you, Thiago, very much. I'll just pull up my presentation. Very happy to accept this invitation, Thiago. I think I speak on behalf of all of us, myself, Odile, and Ana. It was actually almost impossible not to accept your invitation, given you had some time with us recently. It was a face-to-face invitation, but of course one that we're thrilled to accept. I'm going to talk for about 25 minutes on the area to do with modern contemporary painting conservation. It's an area that has been a real focus for our overall research into modern and contemporary art. In fact, it started quite a long time ago. It's getting back to almost a 20-year project. So it's actually one of these very nice projects that's initiated with all kinds of things. In fact, there are so many people all around the world now working on various aspects of the conservation of modern and contemporary art. Which means, in fact, our role is a little bit less active. We've actually moved on to many other things that you'll be hearing about in just a second. It's probably quite hard to make out this image. I'll show the actual artwork a little bit later. This is a detail from Jackson Pollock's extraordinary and enormous painting mural that came to the Getty for conservation a few years ago. This is not me in the slide. This is my colleague, Laura Rivers from the Getty Museum, who's, as you can see, undertaking some conservation treatment on this work of art. I just will start with a few very, very broad and basic concepts that actually I think are valid for almost all contemporary art that is out there, or the vast majority of it. I'm talking about painting, so I'm going to talk about these terms within that context. But most of these, I hope, also set up a bit of introduction for our other two speakers today. There is a huge and diverse range of new materials and processes. This is obvious to anybody, I think, who starts to even wander around a gallery and look at all the materials that have been used by contemporary artists. This is a very, very different period to traditional art forms, which, although many materials were used, the choice was far more limited. many of these materials are inherently unstable or fragile. It doesn't mean all of them are, but I think most of the clear concerns with contemporary art is when a plastic or an audio tape or something deteriorates very, very rapidly, and it's a struggle to know how to deal with that. As if that wasn't bad enough, in many types of contemporary art, there is an expectation somehow that things remain pristine forever. There can be this extremely low tolerance to any kind of sign of age, which makes conservation far more difficult as well, as you can imagine. And often the pressure is therefore to intervene, perhaps at a slightly earlier point than might be considered with other periods of art. As conservators, one of the biggest challenges is that despite all the research and scientific analysis you do on a work of art, when you come to actually undertaking a treatment, any conservator out there will know it doesn't always go to plan. There's a big gap sometimes between theory and practice, and with a lot of contemporary art, modern paintings included, the treatment you undertake is often the first time the artwork has undertaken treatment. So this is the time for any artwork that most of the problems, most of the damage, most of the change is going to happen. Once something's been cleaned 5 times, if you clean it again, the chances are all the very difficult parts of that cleaning have been experienced already. And there are also some extremely complex, what you might call ethical dilemmas. This is often to do with artists being alive, trying to understand a concept or an intent of an artist, and also knowing how to put that into context too. The fields put a lot of work into this, and I know in previous sessions of this conference you were talking about that too. For paintings, and I put there are many words on the first few slides, and then it gets lots of images and pictures, so it should be nicer to look at. But with paintings, the range of materials is very, very obvious and very real. There are so many different types of binders, pigments, and a whole range of additives that are added to most paint types. These all mean that there's essentially an endless number of variables. So it's just impossible to sort of methodically go through different changes to paintings and understand the effect of each of the materials that are in them. Of course, I'm saying some obvious things here, but I want to make sure that anyone that doesn't know this is aware of this, that artists use things that are not intended for them sometimes. And certainly with paints, so many artists have turned to industrial paints, house paints, and not the more expensive paints that are labeled artist paints. The formulations of these paints are often very proprietary, especially with industrial coatings. So that makes it very hard for us to understand what's in them. We have to develop a whole range of analytical techniques. And when you get down to the tiny amounts of additions from additives, not only do you not know what you're looking for, you're trying to find it in very low concentrations. So it's actually extremely hard to do this full characterization. And the reason this is all important is that every different combination of chemicals will lead to differences in properties now and in time with age, and how they respond to treatments and in fact the environment too. Just a visual slide to pick on 3 of the very common types of modern paints used on artwork, and just an obvious visual of the difference in properties. These paintings were created in 2005 by a German artist, Christian Frosch, who I worked with a little bit when I was in London at the Tate Gallery before I moved to the GCI. And he made these artworks by taking 2, as you can probably see, 2 blank stretched canvases and sandwiching paint between them, and then he'd pull them apart, and the paintings were then displayed like this. And it gives a very, very clear visual of the properties of oil paint with its thick and viscous texture. We often call it buttery texture, the texture of butter. You move to acrylic, the waterborne dispersion acrylic paints, which are arguably the most commonly used synthetic paints out there, and they flow much more rapidly. They tend to level out. However, there's still some impasto being created. And then you move to an alkyd-based house paint, one of the most commonly common forms of oil-based house paint. These are designed to flow and to flow to very, very flat surfaces. So you get a very, very fluid and flat finish. It's really hard to generalize about the sorts of paints that are being used, but I've attempted it here. And so this is what I would consider the main classes of paint binders in modern paints, both in artist paints and house paints. There are endless numbers of other things in both lists. And in fact, you know, alkyd, for example, a major part of house paints can be used in artist paints too. So they do crossover, but this gives you a sense of the sort of perhaps, I don't know, 85%, 90% of all paints that are out there. These are two early adverts being used, I think, both from the 60s. The one on the left, the squeeze one is maybe a nice thing to think about on a Monday morning. And I always like this one on the right. This was a UK paint firm, ICI, whose symbol for their house paints was this Old English sheepdog, which presumably is the last thing you'd ever want near your door as you're painting it. But somehow they managed to get this amazing connection with a lovely, floppy, hairy dog and house paint. With all these choices, of course, artists have many choices to make, and I've just listed a few of the reasons. Again, it's really hard to understand every single case, but of course, the things that could make an impact are optical reasons. Paints look very different and have a different gloss and transparency, etc. There's some very practical reasons. Sometimes drying time really varies a lot between the different paint types. Which allows wet and wet or wet on dry. If the diluent is water, that has obvious advantages over organic solvents. There are economic reasons. House paints, of course, tend to be far, far cheaper than artist paints. That can be a big factor. And there are many symbolic reasons. This sort of period where many artists were breaking with tradition, and some of the traditional artist paints were seen as part of that issue. A quick check on time. The work we've done at the GCI, the Getty, as I said, has been quite long running, and essentially we were trying to do three things. The first was to establish methods of analysis of all types of modern paints, and this has largely been done, and it wasn't just done by us. As I said, lots of people around the world are working on this now, but it's obviously the fundamental part of all research, so you can actually analyze and identify things chemically. There are a few pieces that are still in need of some work, but that's been quite satisfying to see. We were quite keen to embark on a study of the physical properties of paints. It's one thing to understand the chemistry, but in fact, often if a painting cracks or is sticky, that's more of a concern to conservators. So it's actually an area that we're still quite involved with, looking at how those things alter with certain conditions. And then thirdly, we wanted to do a treatment study. I think many people will be aware that so much work these days goes into technical study within that sort of heritage science banner. And it's much harder to get these longer term projects looking at treatment. So we did embark on quite an ambitious study of cleaning techniques for acrylic paints. It was thought to be the most common treatment on the most common sort of synthetic paint. That's why we made that choice. So this goes back a bit, but the GCI has been doing a lot of publishing. So I'm giving you 25 minutes of what is probably a 20-year project, or series of research. Lots of people have been publishing, but we've tried quite hard to publish sort of more seminal works and important bodies of work. So I've just put two up here. The one on the left was a symposium held in 2007 at the Tate, just before I moved to the GCI. And it's still, to me, the starting point. If anyone wants to understand a bit about the concepts and see who the main researchers are, it's still really valid. And on the right is one of many PhD theses that we've published, this one on house paints, which has been extremely useful. I will just point out that a lot of these on the Getty website are free to download. So the two I've just showed you, Modern Paints Uncovered, this is a link. You can download the PDF. It's true as a house paints. Not every single one of our publications is PDF downloadable yet, but we're working quite hard on that. But so many, it's actually, if you go on the Getty website, and I'll give you the address at the end, there's all kinds of things that can be downloaded for free. It's not just us publishing. So this is one sort of group of people in Europe based out of the Netherlands who've really been leading the charge on looking at modern oil paintings. So two publications have come out quite recently based on symposia, both in the Netherlands, and they are well worth the read if you're looking at modern oil paint issues. So today, and I'm pretty much on time, I'm just going to spend the rest of the time talking about three specific projects that we've been engaged with at the GCI. The first is a technical study that we undertook on a group of paintings from the concrete art, if I can use that term. I know it has lots of small bits and large bits, but the umbrella term of concrete art in Brazil and Argentina, that we actually did in collaboration with groups in both of those two countries. I certainly want to give a very brief overview of this research we've done into the cleaning of acrylic paintings, because it is, when you ask most conservators, it's fine to hear about how art was made, but they want to know how to treat them. So I'll give you a very brief overview of where that ended up. And if I'm strict with myself and stick on time, I'll have time to talk a little bit about the Jackson Pollock mural painting that I showed right at the beginning. But if I don't, that may not be covered. So the technical study on the concrete art projects, the GCI's involvement was based around an extraordinary collection that many of you will be familiar with. That's of the Patricia Phelps de Cisneros collection. Recently donated, a lot of it recently donated to MoMA in New York. But for 3 years, we were able to do a very in-depth technical study on some of the key pieces in her collection. And we did this very much in collaboration with the two teams from Brazil and Argentina. And there were many, many museums and collections and centers as part of that. So I can't mention all of them, but it was centered around the UFMG in Brazil, with Luis Souza leading that. And the National University of San Martin in Argentina, Fernando Marte was leading that group. And I'm just going to, I think I've got 3 or 4 examples of some of the things we found. It was a very satisfying study in that so little was known about the paints being used by this group of artists. It was known that they were using industrial paints as well as artist paints, but beyond that, there was no real knowledge. And we found an example of every single sort of synthetic paints in our study. So Judith Lowand, this is a more straightforward acrylic paint, artist acrylic, we think applied by a roller. You can see this is the painting, and here's a detail of this area here. The sort of mottled effect that you typically get from a paint roller being applied over a piece of plywood. One of the many Flamingis we looked at. This is the sort of official photo, but if you shine a light into the painting to get a sense of the gloss and the matteness of the surface, you can see it's very, very varied. And there was huge differences in the amount of binder to pigment in the gloss and matte areas. It was a house paint based paint, an alkyd paint, but had pine resin added to it to bump up the gloss in the glossier parts. And then I think actually there are 3 examples. I think this is my last example. Geraldo de Barros, who the surface of this painting is so smooth and so without brushstroke, so clearly some sort of industrial coating. He often polished the surface too, and in fact the analysis showed a very unusual composition of a urethane modified alkyd. So I'm sorry to the translator having to do that. I think you know my technical terms. But he actually, the story behind this painting was quite intriguing. He lived with one of his housemates was another artist, Casma Feyer, who was a chemist and liked to make paints. And we think this is one of the experimental paints that was made at that time. And it actually is lasting very, very nicely. Okay, 7 minutes to go. This ended, the study ended with a exhibition at the Getty. This is one of the views of the installation, with these beautiful pieces spaced around the gallery. And don't worry about reading the text. I've kind of covered that already. And we did make a point of including the technical study. So these are 2 areas talking about the different paint types and the use of a straight edge, in fact, on the right part of that, with accompanying videos and close-ups. And it ended up being extremely popular. The 2 publications came out of this. On the left is the exhibition catalogue. You can also find this on the Getty website. And on the right is actually a placeholder. There's been quite a large scholarly publication coming out from the study, involving many more people from the 3 countries, but including our Argentinian and Brazilian colleagues. And this is just the cover may not be the final cover, but this is coming out, we hope, in the next few months. So switching completely to the studies on cleaning acrylic paints, this has been probably a 10-12 year project. So there are huge numbers of publications out there. We did this largely in collaboration with the Tate in London, where I came from, and when I moved to GCI, the project kept running in a very focused way. Typically when you look at these cleaning studies, you're doing this. You're perhaps rolling a swab over a standard paint out, and you're comparing something, if it's a surface or a chemical composition or an optical property, before and after that cleaning process. And if you compare different paints, you're trying to keep everything the same, and you're trying to roll the same amount of time and the same pressure. It very, very quickly becomes apparent how impossible that is to cover all the different potential cleaning systems. So one of the sort of unusual things that we did was to partner with a big industrial chemical company, Dow Chemical Company. They test paints the whole time, and they use a whole range of what's called high throughput testing methods, HTP, which are essentially it's a way of using robots for this. And without going into too much the details, what you can probably see is this is a piece of metal, piece of aluminium that has a white titanium white paint on it. It's then had some dirt applied to it, artificial dirt. It's all been dried, it's all been aged. And then this is the actual cleaning test. So each of these cotton things is a cleaning test. The solution is actually poured into the little wells up here. It's done in multiples. So these 12 cleaning swabs are all the same cleaning system, and then these 12 behind it are something else. And you can see this is cleaning very well, and this is cleaning not very well at all. And obviously, this is not how you clean a painting. So we had to try and build in all that reality check to our research. But what it did allow was testing of huge numbers of variables in different cleaning systems, and that in combination with then sort of trials with conservators led to some interesting facts. I'm just going to show, well, 2 of them, but based around one concept, and that's the importance of conductivity and pH in any sort of aqueous system. This is fairly well established now, but when we were doing this research, it was really quite new. This is a graph that actually came out of some work done by Richard Wolbers, who also worked on this for a while, where he plotted these three-dimensional graphs, and this axis is the amount of swelling that you would measure on a paint sample. This is the pH and this is the conductivity, and you can see these sort of trends and patterns emerge in this particular paint. The swelling increases quite dramatically when the conductivity decreases, and the same with pH. As you go to alkaline pH, the amount of swelling increases too. So it's just, and of course every paint behaves differently, so it's not like there's a perfect pH conductivity measurement, but it just shows you how important those two concepts are, and that's been fed into all the current research, I think, in cleaning. This is a much simpler way of showing the same thing. So this is a piece of prime canvas with some titanium white put over it. It's shot in raking light, as you can probably see, and then just a drop of deionized water set at conductivity of 6 millisiemens and conductivity set at 20 millisiemens, so conductivity increasing across here, and you'll see that the amount of swelling visibly decreases. So if swelling is one of those concerns you have with cleaning a painting, it's something that you can play with very, very effectively. The other one of the other things we did is that it's amazing now that you can apply analytical measurements to actual cleaning systems. You know, in the past you used to have to immerse things and do quite extreme treatments. This is, and I'm not going to go into the ins and outs of FTIR right now. If you know the technique, this will be familiar to you. If you don't know the technique, it's just a way of creating a fingerprint for different materials. And in this particular material, the acrylic paint seen here has a peak here that vanishes when all the water cleaning systems, these are all water systems, are used. And the only thing that does not affect this peak is a Stoddard solvent, an aliphatic, largely aliphatic mineral spirit salt solvent. So this is done with swabbing. So this is an actual paint film. You take a measurement, you swab roll for, I think it's 10 seconds or 20 seconds. Take another measurement. So you have an in situ real way of monitoring what you're doing to a painting surface. So it's becoming very, very effective, some of the things that can be done looking at cleaning systems. And we, oops, that is my time up. And we have taken this out to a number of places, largely with workshops now. So this is where we find the best outreach is done. With conservators. The most two recent ones we did, one was in Argentina, one was in Brazil with our two colleagues I've mentioned before. So this is the group that was in Buenos Aires at the Torreya Art Conservation Studio, and here's the group at UFMG. You'll probably recognize some of these people, so I'll leave this one up just for a second. And if you want to know more about CAPS, then I'd get in touch with these people. Tiago, that's my time up, so I think I should leave it there, and then if we have time at the end, we can come back to Pollock unless you tell me to keep talking.
Okay, thank you, Tom.
Yeah, thank you so much.
Yeah, thank you. So now we have the talk of Odil's talk.
Hi, everyone. Can you hear me okay? I have my mute off. Success with Zoom. Thanks very much to Tiago and Luis for inviting me to speak today, and for my colleagues. We're excited to be a part of this meeting today. I am a scientist and a conservator, and I'm going to talk to you today about characterizing plastics. So we have a lot of plastic materials. Plastics have been around about, 150, 170 years now. And they now are in every museum collection, every museum, every zoo, every natural history museum, all kinds of collections now have plastics. It's not just art museums. And we're finding that we don't have as much experience with them as we do with more traditional art materials. And we're finding that they don't last as long as the things that we had, the older things that we have in museums. And that's partly because ceramics, bronzes, glass objects that we have in museums are older and they're the survivors. But when we're dealing with plastics, things get nominated to cultural heritage status that haven't had a chance to age. So some of them, if they were traditional materials, they would have gone back to the earth already. But we are charged with stewarding materials, whether they're stable or not. And a lot of what we do comes down to figuring out what plastic is it? What is this stuff? And Tom touched on that with the paints. There's an incredible variety of what you can do with polymers and additives and how you process them that affects everything else you do, how you store them, how you handle them, how you treat them, and also for technical study. So I thought today, instead of talking about a lot of analytical techniques, as Tom also opted not to do, I'm going to talk about my philosophy of how I approach a plastic object. And I'm going to go through some concepts, jump around a bit, and then end with a fun technical study. So, which button? No, remind me which button I push. No.
What do you want?
Which button do I push to go?
Maybe to click on the
There we
right.
go.
There we go.
Yeah.
So what is a plastic? The fundamental component of a plastic is a polymer, and that's a long chain molecule that usually has a carbon backbone. Here's an example. This is polyethylene. These are 3 strands of polyethylene, which is one of the most common commercial plastics today. And each of these chains would extend off thousands, tens of thousands, 100,000 units in either direction. And you can see that we have I'm going to pull up my annotation tool, my mouse. You can see here that we have a backbone of the polymer. So that's the chain, and that's made of carbon atoms. And these white atoms are hydrogen. Polyethylene is a pretty waxy substance, doesn't interact with water, doesn't hold water, water beads up on the surface. It's very low density because these hydrogen atoms are quite small, and they don't restrict the movement of the polymer. So it has, it can be quite flexible. Okay, come on. What am I doing wrong here? There we go. It's just taking a while to respond. The material properties of a polymer depend on the atoms present and their arrangement. So we saw that with polyethylene, we have carbon and hydrogen. Now, if we just swap out some of these hydrogens, can you see my mouse? If you can just swap out some of the hydrogens with chlorine atoms, you have polyvinyl chloride. And that's a very rigid plastic. These chlorine atoms are bigger and they restrict the movement of this polymer chain. They also are something that you can detect analytically. So I'm going to show another molecule as well, another polymer, polyethylene terephthalate, so your drink bottles, soda bottles. You can see it's got a very different chain structure. And the overall pattern of the molecule, you can see it's very different. They're each very different. You can detect that pattern in techniques like FTIR and Raman spectroscopy. You can also detect individual atoms of certain kinds, heavier elements, like the chlorine atoms. And there are certain kinds of groups along a polymer chain, like a benzene ring, a carbonyl group, that also show up and give very specific peaks in an infrared or a Raman spectrum. So that just gives a little introduction, a little hint at where we're going in a case study later on. These polymers often aren't useful by themselves. They make a gooey stuff, but they don't make one that's very useful. Maybe it's not rigid enough. Maybe it's not flexible enough. Maybe it isn't transparent enough, or it's not the color that you want. So smaller molecules are added to change the properties of the final plastic material. One sec, there we go. So here's an example of polyvinyl chloride. This is an idealized example. You can see it's a very rigid looking material. Everything lines up very well. We hear a lot about plasticizers and plasticizer migration in conservation. It's a problem. Plasticizers are added to make plastics less rigid, also to melt at lower temperatures. These are plasticizer molecules. They fit in, this is the phthalate, they fit in between the polymer chains. And what they do is spread them out. And they're not covalently bonded. So over time, they tend to migrate out. These are also molecules that you can pick up analytically, and you can trace their movement in a plastic. So I think about these things when I'm looking at a plastic object. Then there's the processing. It's not just the ingredients, it's how they're worked with. There's the cake, the ingredients, and then there's how you bake it, how you mix it. So these are polystyrene objects. This is a CD jewel case. The front cover is polystyrene. This is the old hamburger case for McDonald's. It is polystyrene. Expanded polystyrene foam is the kind that's a big problem in the environment today. And styrofoam is also in a different form. Bubbles are blown into the polymer to make, in the molten polymer to make a foam. It's made into a construction board that's much more rigid. So the processing really matters. These foams are very different from a CD jewel case. So how do we characterize plastics in conservation science? The thing I start with, after thinking about the chemistry, I think about history, and there's an element of connoisseurship. If you know some history about plastics, you're going to be able to do a lot with deductive reasoning. And connoisseurship, seeing more plastics, experience with more plastics helps you identify plastics. Some people are very good at this. At the GCI, we have a plastics reference collection that is built largely on a donation from a British collector named Colin Williamson. And Anna Lagana, who's speaking next, was instrumental in getting us that collection. The earliest plastics are natural materials. They're natural polymers. They're just made by biology. These objects are very plasticky feeling when you're in person with them, but they're actually made of animal horn, keratin, that's been compression molded into a form, into a shape. So they're actually technically not what we would call plastics at all, except they behave the same. So I tend to consider natural and synthetic plastics polymers interchangeably. Then we move on to semi-synthetic polymers. From about the mid-19th century through World War II, biologically derived plastics were really common. They often simulated natural materials. So here we can see cellulose nitrate in the top imitating tortoiseshell. We can see cellulose nitrate in the bottom right imitating ivory. And on the left, we see a plastic made from milk. This is casein formaldehyde. So another agricultural product, a protein that is made into a plastic. Then in around 1950, after World War II definitely, petroleum extraction improves. It develops very quickly, and pipelines are built all over, I imagine all over the world. This is a map of them in the United States. So petroleum and natural gas are shipped everywhere, and all of a sudden it becomes very feasible to make plastics out of them. I've got a fun example from 1958 with polyethylene, natural gas with a catalyst from Phillips Petroleum. I think it was, I want to say it was chromium catalyst. All of a sudden you could take gas from the air and you could make it into a goo. And at Phillips, they thought this was really fabulous and no one used it. And about 8 years later, Wham-O, the toy company, made a hula hoop and out of polyethylene. And 100 million, more than 100 million of these sold worldwide in 2 years. So you've got polyethylene off and going. From there, it and polypropylene have expanded to be the most common commercial polymers in the world, and other petroleum and natural gas-based polymers as well. On time, okay. So can we teach connoisseurship? We can teach history, certainly, but can we teach looking at plastics? At the GCI, we're really lucky now to have this great collection of old and new plastics that represent all sorts of polymers, all sorts of manufacturing techniques, different additives, and different condition. That's important. We can see what problems are representative of certain kinds of plastic. And when we want to know what a plastic looks like, either we've seen a lot of them already and we kind of recognize some of them, or we can go and look for examples. We can also use these objects to collect reference spectra. We can show them to our various analytical instruments and record that data. So later on, when we analyze an unknown object, we can compare it to things in the reference collection, and that helps us identify what we have. Not everyone has reference collections. This takes a lot of effort to get, and we are very fortunate. So some groups have been working, doing some really clever things to teach connoisseurship. First, there are workshops. Tom touched on the CAPS workshop for painting, cleaning paintings, acrylic paintings. GCI also hosts a couple plastics workshops that are taught around the world, and other groups do as well. There's a new tool that came out, I guess last year. I saw it at a talk in Future Talks conference in Munich. A group in the Netherlands has come out with something called it's actually the plastic identification tool. And you can look that up online. I put the website down below. I put our website down below as well. The plastic identification tool is an online tool that does a question and answer. It offers a few tools in there, but the one I like best is a question and answer. And I'm sorry, they wouldn't let me grab a screenshot of their questions, but let's say you have Sophie La Giraffe, the rubber Sophie. It might ask you, is it flexible? You put yes, no. And it says, is it transparent? You put yes, no. And is it crumbling? Yes, no. Does it smell kind of sweet? Yes, no. And at the end, it gives you a probability of what kind of plastic you might have. And on a scale of 1 to 100, it tells you the likelihood that you have a certain kind of plastic. And that's really useful. There is also a glossary of different trade names. So many plastic trade names are included. And they are selling a 50 sample reference kit called the PIT kit. So they have amassed 50 samples of plastic and put them in a toolbox with some tools for testing them. And one can buy those. They are available for purchase. So if you're interested in that, I encourage you to check out the website. The plastics identification tool seems to be an evolution of a project that was from 2008 to 2012 called the Pop Art Project. This was a European initiative, a large European initiative to study heritage plastics. And they studied all sorts of things, characterizing plastics, cleaning plastics. It's a fabulous project. Again, the website, the French version of the website is down below. Two things I like very much in it are that they produced a damage atlas. So you can go to this website and find the damage atlas, and it will show you images of different kinds of deterioration of different kinds of plastic. So if you see something, you can go and match what you're looking at. That's really useful. They also produced something called the SAMCO, Samples for Conservation is what I think it stood for. It's a reference kit of plastics. It was available to the group members, and now the plastics identification tool has created something very similar that they are selling and make available to all of us. We're lucky that we have a SAMCO kit because Anna Lagana made it. So we're very lucky, and we were part of the GCI was part of the Pop Art Project. So we're very fortunate to have one. But you see here, there are different kinds of plastics that represent the most common kinds and the processing that you'd expect to find. So I've shown you specific objects, reference objects that are either an actual artifact or they are a fragment of a kind of plastic. That teaches you a lot about what's out there. It teaches you what plastics you might encounter. It teaches you about representative problems. What problems are typical of this plastic? What it does not do is allow you to reproduce any kind of experiment. So plastics, let's say a plastic has 5 components and you don't know which one is the problem. It would be really nice if you could make a plastic with just 2 components. Start with one polymer, then add a plasticizer, add another plasticizer, add more or less of a plasticizer. If you could do that and make your own plastics, you could do all sorts of experiments of, you could create reference spectra. You could create samples that you could distribute to other groups. You could do cleaning tests. You could do aging experiments. And so at the GCI last year, we invested in a setup of equipment that allows us to compound and extrude and mold our own plastics. This is the extruder. It's a twin screw extruder down below on the left. We add polymers, and there are ports in the top. We add polymers and various additives in the holes at the top. There are two screws inside that turn and mix the material together. And at the end comes a plastic strand that looks a lot like spaghetti. We have a rotating knife that cuts it into little pellets. They're often called nurdles. And then we have an injection molder that melts those pellets, forces them into a metal mold, and gives us a certain shape. So in this case, we end up with some plastic tabs, a pair of them that we can compare. And here, we have a dog bone shape as well right here. And a couple of things I like about this project, I've described that we can reproduce, we can make experimental materials. We're also learning a lot about fabrication. How does fabrication affect the plastics aging characteristics? So what if it got too hot? What if it sat in the molder too long? That's all very useful to us. We're also able now to combine chemical analysis, so identify something with spectroscopy, and then mechanical testing. So in the lower right, you can see that we can cast a bar, and we can then use equipment to bend it and see if there are changes in the flexibility, either with changes in composition or with changes in time. So the scientific analytical methods tend to get a lot of attention at scientific conferences. And there's a wide range of analytical techniques that can teach you about the molecular composition, the elemental composition, that can image plastics. And that's all come along really well in the last couple decades. I will say that sometimes the analytical methods seem like, oh my, that's what you should do. You should rely on science. And really, I don't find that to be the case. Without the information I've already shown you, the history and the connoisseurship, understanding something about the plastic and how it's been made, you don't really know what to look for. So getting data can give you an answer, but it's not necessarily going to give you the full answer. So for example, with polyvinyl chloride or cellulose acetate, it's very important to know that in the case of cellulose acetate, always, and in PVC, if it's flexible, if it's an object, there's a plasticizer involved. There is one of those plasticizer molecules included. You need to know that. So I encourage you not to shortchange the historical and connoisseurship information. So these are my go-tos. These are the typical techniques. There are so many that you can use to look at plastics. These are my favorites. I rely on finding the polymer using Fourier transform infrared spectroscopy, FTIR, and Raman spectroscopy. These can detect down to percent concentrations. They're not incredibly sensitive, so they teach you about the major components of a plastic. They don't teach you necessarily about tiny traces of antioxidants, heat stabilizers, small amounts of degradation products. They will detect a plasticizer, and Raman spectroscopy will be able to distinguish the phthalates, whereas FTIR will just tell you you have a phthalate, for example. Infrared spectroscopy can show you some inorganic materials like calcium carbonate, but Raman spectroscopy is really good at it. Both techniques are potentially non-destructive, although FTIR often requires removing a sample, and Raman spectroscopy has the possibility of burning it with a laser. So one needs to take treat these techniques with some caution, be circumspect about it. Pyrolysis gas chromatography and mass spectrometry is the technique I go to for looking for trace components, smaller amounts of material. It is destructive, and you put a sample in an instrument and it will tell you the organic composition. It'll tell you what's there. X-ray fluorescence spectrometry and scanning electron microscopy can tell you the elemental composition. X-ray XRF is non-destructive. You can look at an object in place. There are portable instruments. SEM requires putting an object in a chamber. That's more, so the object either has to be small or you have to take a piece of it. I will say with SEM, looking at plastics, that's pretty, I'm speaking now to the people who are interested in these techniques. SEM is challenging with plastics because the electron beam tends to damage the plastic, which hurts your data, hurts the image of the surface. So SEM is usually an imaging technique. It starts to pit the surface. We've had a lot of luck by sputter coating plastics with conductive metal layers first. We can use gold palladium, silver would work. That's been really useful. And then there are imaging techniques. We want to look at, we don't just want to know what the composition is, we want to look at the structure. I like using my eyes and microscopes and the SEM for the surface. You can do chemical mapping with some of these techniques, but taking an X-ray is fun. It shows you the construction of the object. Is there an armature inside? Are there bubbles? And it can also, as I'm going to show you in a second, it can help you identify the plastic. A computed tomography or X-ray computed tomography is a 3D X-ray. So, and now I have a case study that involves, I found one that includes 4 of these techniques that I'm going to cover now. So a few years back, some UCLA students brought me a Barbie doll. And Barbie, to some laugh, Barbie happens to be until recently, it was $1 billion a year industry worldwide. It certainly makes hundreds of millions of dollars a year now. And many of us remember this from our childhoods. The early examples are very collectible now. And they're made of plastic. So they don't, they have problems that tend to, from what I hear, they tend to be specific to certain years. Like a Barbie from one year will have fuzzy legs, for example, whereas a Barbie from another year will have sticky faces. And that's not necessarily, it hasn't shown that they necessarily improve with time. It's just, it's an oddity of the changes in processing by this toy company. Barbie was made by Mattel, a company that has its headquarters here in Los Angeles. And I did this work when I was at the Smithsonian's Museum Conservation Institute in conjunction with the Natural History Museum, National Museum of Natural History there. Some of the writing up was done at the GCI, but the main impetus for the project came from UCLA. So this Barbie's in a private collection, and you can see that she's called a number 4 Barbie. She's from 1960, so she is the 4th version of Barbie. I think Barbie was first made in 1950. I want to say 1958, 59. And you can see this one has a few things going on. She's wearing a bathing suit. She has fuzzy legs, which is problematic. She was potentially exposed to a hot day when the air conditioning broke in the collector's home in Los Angeles. So temperatures reached about 90 degrees, which is the mid 30s Celsius. And you can see that here the artist, the designer Ruth Handler has written her name, and the plasticizer has caused that ink to bleed. So looking at Barbie, the first thing I wanted to know, I suspected she was PVC. I showed you those chlorine atoms. X-ray fluorescence spectrometry is neat in that it can show you elements that are heavier than silicon, typically heavier than silicon. Sometimes you can see some aluminum, but silicon's a pretty safe bet. What it doesn't show you is carbon, oxygen, and hydrogen, which is what most plastics are made of. So you won't see the composition of most plastics with an XRF, they'll be invisible, but you can see chlorine. So if you see a big chlorine peak, you might have PVC. If you don't see chlorine, you don't have PVC. Another plastic that's useful to look at with XRF is casein. As I mentioned before, it comes from milk. So casein has calcium in it. If you don't see calcium, it's not casein. That's very useful information. And XRF is quick and easy if you have access to the equipment. So here we took Barbie and we put her under our RTAX XRF. This was done at MCI at the Smithsonian. And we came up with this spectrum. So you get peaks that are representative of the various elements. And we found that she does in fact have a whole lot of chlorine in her body parts. It was all of them, I think, except her head. And along with some calcium and some titanium. I then, normally with FTIR, if you use there's an ATR, an attenuated total reflectance objective. It's an easy way to just take a plastic sample and squash it down onto a crystal, and you get your spectrum. Instead of taking a sample off the Barbie, I just squashed her foot onto the crystal. You can see that happening here. And we got at the top, you can see a spectrum here, the infrared spectrum of the leg, the foot. It's a continuous single piece. That's got a lot of noise to it, but it gives me the information I need. First, I went and I checked, I compared it to PVC. Yep, it's a good match to PVC. XRF confirms that, or supports that. And I subtracted out this PVC spectrum, and what I got left matches really well with bis-2 ethyl hexyl phthalate, which is also called diethyl hexyl phthalate or dioctyl phthalate, which is the typical plasticizer for PVC. When it oozes out of plastic, it's gooey. Like, I know this from my connoisseurship by having a lot of experience with PVC. It's sticky, and these legs are fuzzy. They're not sticky. So we took some of this efflorescence and we put it in the Raman spectrometer. The FTIR wasn't particularly useful. And here we see a Raman spectrum of the fuzz and compared to sodium stearate. This is a coming out. It's a waxy substance that's a lubricant added to plastics. So these legs, a lubricant is something that reduces friction of the polymer molecules against themselves, of the plastic against the machinery. It makes the plastic less sticky. So if you're going to injection mold a leg that is unnaturally long, as Barbie has really unnaturally long legs, if you want to do that, you don't want it to get the plastic to get stuck in the mold. So it looks like in the early years, they applied a lot of lubricant. And it was too much for the plastic to hold, so it's moving out over time. Lubricants, I know, are only there for processing. I can't think of a reason why they help the finished plastic. So, and when enough of it migrates out, it should stop happening. So the solution was, and was all along, just brush it off. But it's not the same as a plasticizer being lost, which can cause much bigger problems. Finally, I wanted to see the structure of the Barbie. We were wondering if she had an armature, some other things about her. So we stuck her in a X-ray computed tomography, a CT scanner that was at the National Museum of Natural History. It's usually used to look at mummies. Here, Barbie is going into the scanner. We got a lot of fun looking at that, laughing at it. And you can see that a CT gives you a 3D X-ray that you can then, you get these huge digital files that you can then scroll through the object vertically, down from top to bottom, from side to side, across its depth, and you look at slices. So I've pulled a couple slices here to show you her front, or to show her front through from the front and from the side. And we compared her to a Barbie from a couple, let me move my, that's me out of the way here. This is Barbie from a couple years later. I think ours is 1960. I think this comparison Barbie is 1962. And you can see that there are some important differences. I have a minute left. There are some important differences in the opacity of the X-ray. The old Barbie is much more opaque, and the newer one is much less dense. And you can see that in the details here as well. This is there's a detail of the shoulders at the top. What's happened is chlorine is more dense than plastics that don't have chlorine. So PVC will be more dense than, say, polyethylene. And what we see here with the CT is that they've changed the torso. In the course of a couple of years, they changed the torso to polyethylene. This did a few things. It allowed them to use a much thinner wall, right? It makes a much more rigid plastic, and it makes a lighter doll. It's a lighter toy and more delightful to play with. They also changed the arm attachments. presumably they click in more easily to the rigid polyethylene. And here's the pelvis. Oh, we're right at 25 minutes. Oh, I think I'm actually, I think I'm a bit over. The pelvis, the legs, you can see that they've changed the leg design as well. So with that, I'll end. I think that's just, there are many ways to look at plastics. That's just some opportunities, some ways of looking at it, and I'll look forward to your questions at the end. Thanks.
Thank you so much, Jill. So now we have the talk of Anna. Please, Anna. You are muted.
Yes, I've seen it. Thanks, Tiago. Thanks to you and Luis to inviting me. Happy to be here with my colleague. And thanks, Odile, to introducing already some of the things that I'm going to share. And I'm reading because I'm worried that otherwise I will be not on time, then I can control it. Okay. So today in this presentation, I will outline, some of the challenge that conservators face to preserve objects made of plastic and how we are exploring solutions to overcome these challenges. So I will speak about treatments. So as Odile has said before, since their introduction to the market, plastics have been used to make an infinite variety of artifacts and artwork, which currently form a significant part of our cultural heritage. Plastics are present in all kinds of collections, modern and contemporary art, in form of sculpture, paintings, installation, design, fashion, science, ethnographic, military, and much, much more. However, unfortunately, these materials were not designed to last forever. Plastics have proven to have short lifetimes compared with traditional materials found in museum collections and can exhibit visible symptoms of degradation between 5 and 35 years. Plastic can discolor, can deform, can delaminate, craze, crack, warp, crumble, blister, sweat, chalk, weep, and some may even release acidic components. Regarding conservation, the first international conference dedicated to the issue that plastic posed in collection was in 1991. This is considered by many the beginning of the development of conservation of plastics as a discipline. Since then, as pointed out by scientist Yvonne Shashoa, this discipline is progressively developed in cycles. The first cycle started in the 1990s and focused on research degradation pathways. The second began at the end of the 90s, developing strategies to inhibit degradation. And in 2000, the third cycle started focusing on interventing conservation by trying to actively stabilize and treat the symptom of degradation. And today, this is what I will focus on, interventive conservation. Interventive conservation comprises cleaning and other treatment used by conservators to repair damaged or degraded plastics, such as adhering, filling, consolidating. However, currently established treatment for plastic are few opposed to those developed for the conservation of other material. This because the conservation of plastic is a new discipline still developing. There are many difficulties of finding conservation material and method that can successfully treat these plastics without harming them. And also because the development and evaluation of active treatments require considerable time and resources. So today I will highlight issues and challenges that cleaning and repairing of plastics pose. I will briefly present two research studies, one on cleaning and one on filling plastic I have worked on, in order to share the approaches used to identify suitable materials and methods for developing safe and successful treatment for plastics. I will start with the cleaning. Museum surveys have shown that the majority of plastics in collection need cleaning. Most plastic, being electrostatic material, easily attract and gather dirt on their surface. Type of dirt and residues generally include air particles, greasy deposit, fingerprints, as well as additives, such as plasticizer in solid or liquid form, as you can see in the two last slides in the screen, that can migrate from the plastic to its surface to the degradation, and then can attract the dust and dirt. Although it has been shown that cleaning of plastic is often required, this plastic has been poorly developed, especially due to the issue and risk this treatment can pose. Mechanical cleaning can cause abrasion and scratches in some plastics. Solvent cleaning can cause swelling, solubilization, or extraction of plasticizer or colorant, as you can see in the little sample of the plastic in solvents. And in rigid plastics, transparent plastics can induce crazing or cracking in the polymer structure, which can occur immediately or over time. Therefore, in order to establish how risk of cleaning could be avoided, part of the first European project on the preservation of plastic called POPART, that Odile already mentioned, focused on identifying material to safely and effectively clean plastics and establish finally some guidelines. During the POPART project, Studies in Cleaning, a systematic research on the effect and efficiency of mechanical, aqueous, and solvent cleanings was carried out on plastic among the most common in collection, such as cellulose acetate, polyethylene, polystyrene, polymethyl methacrylate, also known as PMMA, and PVC. Cleaning material and agents were selected from those commonly used in conservation and industrial cleaning. For mechanical cleaning, a large variety of materials, including cloth, brushes, sponges, and dusters, were selected. For aqueous cleaning, distilled water was included, as well as different types of surfactants, synthetic saliva, and alkylating agent. And for solvent cleaning, even some considered as high risk were included to fully evaluate the impact of this on the plastics. Cleaning materials and agents were initially evaluated for their ability to change or damage the model plastic using visual observation, gloss and contact angle measurement, and calculating the percentage of area covered with scratches after cleaning. Moreover, their effect after aging was also investigated. Then, those not causing measurable changes and damage on model plastic during cleaning were further tested on their effectiveness to remove soils. Two standard types of soil were used in testing: a waxy soil simulating fingerprints and an organic oil soil. The effectiveness of each cleaning material and agent was evaluated, in this case, only with visual observation. Results of mechanical cleaning tests highlighted higher sensitivity of some plastics, here listed on the screen, compared to others. Many products damaged the plastic and some left residues, while Canadair, natural and synthetic duster, sable airbrush, microfibers, spectacle, and cotton cloth proved to be safe. All the aqueous cleaning agents showed to be safe for cleaning the selected plastics. No change or damage were observed. Moreover, they were effective in removing the oily soil. Regarding the solvent, the effect of each solvent on the plastic clearly depended on its chemical resistance. However, it was generally concluded that white spirit was the safest solvent to use on all plastics tested, while the most damaging ones were acetone and sulfonol. Regarding the effectiveness, ethanol, isopropanol, and white spirit proved to be effective in removing instead the waxy soil. And in general, cloth, spectacle or microfiber, and cotton bud resulted to be the best material and safe to use for applying aqueous and solvent agents on the plastic surfaces. Finally, the results, which included the safest and the most effective materials and agents, aqueous and solvent, for removing dust and soils from the plastic, have been summarized as a set of decision-based flowchart, one for each plastic tested. The POPART flowchart suggested a cleaning sequence, which included the initial removal of dust and loose particles by mechanical cleaning, possible by blowing air over surface, and other cleaning methods listed such cloths or brushes, followed by the use of specific aqueous agent to remove any other fixed particle present or such as oily soil. And finally, as a last step, for the removal of other type of soil, such as fingerprints that can be removed with aqueous agent, the chart suggests solvents that can be safely used on each kind of plastics. Moreover, as you can, it's very small, but you can see in the flow chart, each flow chart includes some recommendation. For instance, extra care should be used on plastics in poor condition, considering the polarity of the plastic can change and therefore its solubility and sensitivity. And include also some more specific recommendation, as for color degraded cellulose acetate, in which the use of alcohols should be absolutely avoided. The last step was to apply research findings on real objects from museum and private collection. Due to the time limitation today, I can't go thoroughly discuss the cleaning of each case study. However, I just want to briefly show the successful results gained using the pop art flowchart to clean 3 objects made of different plastic, as you can see on the screen. The first one on the left, made of PMMA sheets, was heavily covered by a thick layer of dust and dirt. The second object, made of PVC, show a sticky soil, most likely consisting of a plasticizer, which migrate to the surface, attracting dust and dirt. And the third one on the right, an artist's book made of a variety of cellulose acetate sheets, show fixed particle, as well as the presence of white, solid, sticky deposit, identified later with FTR as plasticizer on the survey of the color sheets. All objects were successfully cleaned using the flow chart. The first step for all objects was the removal of dust using a museum vacuum cleaner with the stable brush. Then cleaning tests were carried out with aqueous cleaning agents suggested in the flow chart for each plastics to remove the fixed particle and the oily soil. For the PMMA and PVC, 2 surfactants show the best results, Orbus and Dayphone. While for the cellulose acetate book, the use of a microfiber cloth moisturized with distilled water was enough to remove both dirt and plasticizer deposit. In both objects, it was decided to remove the plasticizer deposit because they collect dirt and they will have continued to do so over time. So to conclude, although the cleaning of plastic still remains basic in its approach in comparison with cleaning methods used for other materials, as we have seen it before, this project remains still very important because it established the first guideline to safely clean plastic, and it creates a baseline for further projects. So and now I'm turning to the issue and the research study related to the repairing of plastics. Establishing treatment for the repair of damaged plastic is also challenging. The main difficulties is to find conservation material that fulfill the criteria necessary for completely successful repair without harming the plastic, as also for cleaning. For instance, many conservation materials generally used to carry out repairs, such as filler or adhesive, contain organic liquid or produce heat during curing that can cause damage to plastics, which considerably narrowing the choice of the material. Moreover, reversibility can also be an issue because some conservation materials are also synthetic polymer like the plastic, making sometimes the reversibility from this type of artifacts difficult. In addition, if damaged plastic is transparent, finding an optimal conservation material is even more challenging because the product should be able also to produce invisible repair, which are very difficult to achieve as evident in glass conservation. As a result, plastic artifacts that are severely damaged, especially those made with transparent plastics, often undergo invasive treatment, entailing the removal of original material. Many are kept in storage, and in extreme cases are deassociated from collection, refabricated, because there is a lack in the knowledge of repairing plastics. Therefore, as a part of its preservation of plastic project, the Getty Conservation Institute, the GCI, is investigating materials and methods to repair losses, scratches, chips, and broken parts on plastic artifacts, with a particular focus on those made of transparent plastic, such as unsaturated polyester and polymethyl methacrylate, given the complex challenge posed by their conservation. So I will now present a short overview of one research study, part of this broad project, the research into film materials and method to repair PMMA in contemporary objects and photograph, in order to show the approach we are using at the GCI to develop safe and successful treatments. PMMA, as you can see here, was commercially introduced as a transparent cast sheets in the early 1930s. And because it possesses the transparency of glass and can be easily shaped, it has been extensively used as an artistic medium to make sculpture and object. And since the 1980s, it was used to make face-mounted photograph. In this type of photograph, as you can see on the right, a clear PMMA sheet is permanently adhered to the surface of a print to add depth and color saturation. However, whereas PMMA is more impact resistant to breaking than glass, it is also more susceptible to surface damages, such as scratches and chips, which generally occur during handling and transportation. These damages can be extremely disfiguring, especially on face-mounted photograph, because they appear in front of the image. The most common treatment option to reduce these damages is polishing, which is an invasive treatment because it is based on the removal of surface material instead of its actual repair. Moreover, polishing is not always suitable, especially when damages are very deep, as the chip you see in the slide, because it entails the removal of a significant quantity of PMMA. Therefore, in order to provide less invasive solution to repair this type of object, this project aims to investigate suitable film materials and methods to repair local scratches and chips without modifying the PMMA surface. Film materials were selected on the basis of their desired properties, aesthetic and physical properties. Material had to be clear and colorless as the PMMA, have a refractive index as close as possible to the one of PMMA to obtain less visible repair, a low viscosity to easily flow into the small damages, suitable working and curing time, exhibit no exothermic reaction, low shrinkage upon curing, and not be harmful to the plastics. PMMA is sensitive to many chemicals. Only water and aliphatic hydrocarbons with low aromatic contents are considered safe to use on PMMA, limiting considerably the type of film materials that may be used. Based on this consideration, 18 products from 4 material categories were selected and tested: acrylic resin and hydrocarbon resin, both dissolved in aliphatic hydrocarbon solvents with low aromatic content, epoxy resin, and UV curing adhesive. Treatment tests were first conducted on samples from clear PMMA sheets which were delivery damaged. Based on the results of previous GCI research, the Princeton round mini brush size 20-0 was used to fill scratches, while insect needles or small glass pipettes were used to fill chips, depending on the viscosity of the material. Fill material were applied neatly within the boundaries of the damage until the loss was filled, taking care not to overfill in order to avoid any later finishing treatment or solvent use. The suitability of film material was determined on the basis of their working properties, ability to recover the lost transparency, and stability. In particular, their potential to improve visual appearance of damaged surface was assessed with naked eyes observation and optical microscopy. The match between the refractive index of the filling product and the PMMA was determined by carried out refractive index measurement. The composition of material was determined using FTR analysis and film of each film material were exposed to 400 hours of accelerated light aging, and their stability was evaluated before, during, and after aging using FTR and color measurement. Based on this evaluation, the epoxy resin Hixtal and YL1 and the hydrocarbon resin Rigaretz 1094 were identified as the best option and used for selected further tests on deliberately damaged mockups, simulating real museum objects, clear PMMA Soviet clips, and a face-mounted photograph. Tests on mockups show that this product restored the transparency on both objects, as you can see in the slide. They were easy to apply and posed no issue during curing. Rigaretz has the advantage of being reversible, while Hixtal present minimal dimensional change upon curing, allowing fewer application when filling compared to solvent-based adhesive. Ultimately, results were applied on real object and face-mounted photograph from museum and gallery collection. Here is one of the PMMA objects from the Cultural Heritage Agency of the Netherlands collection that has been treated. Treatments were performed with object lying flat as well in upright position. This object shows several scratches on its PMMA surface. For treating these scratches, Rigaretz 1094 was preferred to Hixtal because it has the advantage of being reversible with solvent. The resin was easily applied with a mini brush like a paint retouch. One application was sufficient to reduce scratches. The brush was able to hold the low viscosity product, and rigorously successfully retouched the damaged PMMA surface, recovering its transparency, as you can see. Results were also applied on a photograph made of ink onto Zebrachrome face and back mounted with PMMA with a softer, a serious chip. Hixtal was chosen in this case to treat the damage because due to its minimal shrinkage upon curing, it proved easier to use on deep chips than solvent-based adhesive. The object was placed flat on a table and beeswax was applying along the edge to avoid spreading of the resin, and the epoxy was carefully dripped into the chip until it was completely filled. After curing, no further application were required. The repair matched the PMMA surface in level and clarity, completely recovering the transparency and therefore the visibility of the image underneath. Thus, the results of this investigation show that less invasive treatment as an alternative to polishing or surface modification exists for the repair of PMMA surfaces. Film material can successfully improve the visual appearance of local scratches and chips, and the film methods developed eliminate the need for finishing treatments. So, to conclude today with this presentation, I hope to have given you an idea of some of the challenges that conservators, like me, have to face to preserve plastic. And I hope to have highlighted especially how treatment studies are important for the advancement of this new discipline. There are more challenges to overcome, but we are continuing exploring solutions, aiming to increase the number of treatment options currently available to conservators. And I would like to thank all the people that work on this project, my project teams, and all the people listed here on the screen that help and support this research, and all of you. Thanks.
Thank you so much, Anna. Thank you so much, Tom, Odile, and Anna for the excellent talks. So I think we have time for one question. And we still don't have on the chat, so I will do some considerations and do a question I have. Considering both paintings and plastics, I saw something in common. So we have a large range of materials and processes of production. A lot of treatments have not been tested on those materials. We have changes in formulations during history, time, and geography. So in conclusion, what we have is a physically and chemically complex objects. And what was clear from is that chemical characterization is a very important step for the preservation of these objects. But when we think in our reality in Brazil, it is not always possible. So particularly, it is because the difficulties in establishing cooperation between conservators and scientists, and also because the low number of specific facilities and expert professionals to do these analyses. So based on your experiences as conservators and scientists, what I would like to know is how can we make such cooperation between conservators and scientists more effective to preserve these contemporary and modern objects?
Shall I start? Yeah, okay. So I mean, your summary was very good, Thiago. I would just like to say a couple of things about this, because it is very difficult without, you know, understanding resources and different countries, part of the world, and etc. But I think what came across in all our talks actually is the importance of empirical observation, practical observations coming from conservators. The science is very, very helpful in certain areas, and you can apply it, as you've seen, to answer certain questions. But I hope what we're doing is not saying you need that sort of level of an analytical support to do anything at all. I've actually, in the last, I don't know, 4 or 5 years, been to many different parts of the world and had these sort of discussions. And I think what is important and what's nice is that it's not as if the West or the North has sorted it all out and here are some ways to treat contemporary art. There's so many unknowns. It's that it will never be completely understood or anywhere near that, in fact. So the sort of importance of networking and communication with each other. And there's very, very strong networks around the world dealing with contemporary art. I'll mention one of them, Inca, that all of us probably know about, but it's not the only one. And that sort of, being in touch with people around the world who are very, very open to dialogue and suggestions is important. But the other thing, specifically for Brazil, I mean, there are parts of the university that I've seen, that Louise has shown me, whatever it is, many, many different scanning electron microscopes, tunneling electron microscopes. We don't have access to that. So this idea that there aren't facilities in Brazil to the level we've been showing, I don't agree with. I think they're there. And I think, you, Thiago and Louise are busy building these bridges, but it's just, everything's there to be done. You I can't really comment on how you would communicate better with conservative scientists in Brazil. That's entirely, your thing to do. But I don't see any problem with, I don't see any fundamental problem with what you have to do.
You are muted, Jojo.
There we go. It's always a problem for me. I agree that the university resources seem excellent in Brazil. And Thiago, you're an excellent Raman spectroscopist. I think one thing that was nice about having you at the GCI is that you work with cultural heritage. And so you're interested in that background information, understanding what is different about industrial. How is cultural heritage distinct from industrial questions and academic questions? So I really do think a lot can be done without analytical instrumentation. I'd like to point out a couple of things. Anna, when you were talking about pop art, there were a couple solvents used for cleaning that seem to clean a lot of plastics. So there are some treatment options that can be more universal. There are online tools like the plastics identification tool for questions. Yes. Yeah. And MoLab is I don't know if you've heard of this. In Europe, there is a mobile laboratory that is put together by, it's European, where groups can make proposals to this group of experts with portable instruments. I think they have like 13 different portable instruments and a van. And they take that, they accept certain proposals each year and take the equipment to the project. And I wonder if that could be done in South America. Portable instruments, yes, they're expensive, but can it be done? Could money be raised to take something that could then bring the lab to your project?
If I should point out without a deal that Hyperion, which is the current umbrella under which these mobile labs sit, Brazil is a member of that organization now, so it's absolutely part of the discussion.
We have a question in the chat. I think we can do. It's from Beatriz. How to make a connection between research and practice in the restoration? Many times I need scientific analysis that are not used to do on works properly. Yeah, so this question is, I think, is related with what I meant on. So we have the infrastructure, but we don't have enough infrastructure for everybody that needs this analysis. So I think that Beatrice is trying to ask something related to that, how to make this connection. And I think that Tom already answered it. Yeah. So unfortunately, if you don't have any more comments, unfortunately, we need to end this session because we are on time. And so I would like to thank you again, Tom, Odile, and Anna, for sharing all this knowledge with us, and looking forward to see you soon.
Thanks. Thank you very much.
Absolutely. Thank you, everyone.
Thanks.
Bye-bye.
Okay, so thank you.
We off.
Now have a rest, a 15 minutes rest, so that people can go have a water and take their time. We are starting again in 14 minutes. So the room is free.
So
we cut the session, so now it's informal. So we can
just us now. Okay.
Yeah. If you are there, that's fine. I mean, people have questions, and we can continue on an informal basis. We are on a break now.
Okay.
Great.
I have to apologize. I ran over. I forgot to set I didn't work my stopwatch very well. I'm really sorry about that.
No, you were on time.
I think I was about 3 minutes over, but sorry about that.
That's okay.
Oh.
All right.
Luis, there is a question on the. Can I make the question?
Yes. So because we are on the break, the translation is not there, but you can continue in English, and then we just chat with them to translate. That's no problem.
Okay. So someone wrote, "Thank you so much for the presentations. I would like to know from Anna and Odile if they could explain what happened with the use of the cola superbonder. Is the what's the name of the polymer, Luis? Do you remember? Polyacrylate, yeah. In acetate, in the case to bond broken parts that cause an effect of like a smog or a fog, effect of fog.
Off-gassing?
Probably, yeah.
Maybe the off-gassing.
Yeah, on the surface of the material. Why that happened and how can we remove that when you apply this?
I think I know what she's talking about. It's like when you have like a whitish transparent layer on top of the plastic.
Anna, do you want to start?
With cyanoacrylate.
With it's maybe polymethyl methacrylate. Is the acrylic? What is or any other transparent things?
It's in the cyanoacrylate glue.
Ah, it's in the
Okay,
I thought it was the original material. So it's a cyanoacrylate glue.
Does it get? You mean that does the cyanoacrylate glue get hazy?
Oh, she's saying that is Loctite super glue with acetate.
Oh,
Now I read in the Portuguese. Esse cara, super good.
I think I know what it is. When she applies the cyanoacrylate
On acetate, okay.
on top of acetate, it gives this whitish veil. It's probably because of the solvent that it's acting on the plastic material. So then it becomes whitish.
Yeah.
Hein, Thiago? Aí você pode explicar em português, né? Que quando aplica
Sim,
a cola...
Vai lá.
Yeah.
Voila.
Is cellulose acetate the material? Yeah, probably. Yeah, it's not the right adhesive. I mean, another adhesive could be better used. That is maybe the reason. Yeah, the reason.
O que a gente... Oh, sorry, Ana.
She mentioned remove it. How can she remove it? One thing I noticed with Anna's polymethyl methacrylate work is that sometimes the white haze isn't something sitting on the surface. Sometimes you've got material sitting on the surface that you can wipe off. But with the PMMA that Anna's been working with over the years, it's actually a fine network of bubbles in the plastic. Anna, do you want to talk about that?
Yeah. So in some cases, when you see haziness on the plastic, it's just actually tons of small voids. So that's why there are an agglomeration of small voids. And so this is, you don't see, the light is not scattering anymore in the same way. So the material, instead of looking transparent, it looks white, basically, really in a basic way. But something happened with the surface of the material. So,
yeah, and you can't wipe it off.
No, it's nothing on top of the material. It's not a thin layer of something. It's really the surface they change. And so scattering differently. So there is a change in the material itself, and it's not reversible.
Então, o que a gente entendeu foi que foi aplicada uma camada de super bonder numa superfície de acetato. E aí a possibilidade de explicação seria que você tem uma modificação na superfície que vai causar essa refração da luz de um modo diferente, que causa esse efeito esbranquiçado. O que a Ana e o Odilo estavam falando agora era sobre a superfície de PMMA, quando você tem também esse efeito, que é essa doença, entre aspas, de embranquecimento, que o que acontece basicamente é uma degradação física no material que também causa um efeito de espalhamento da luz de uma forma diferente, que causa esse embranquecimento na superfície. Qualquer questão a mais, podem, por favor, colocar no chat. Yeah, and Anna, are you still working on that project? Are you changing formulations now? What step are you working on that?
For the PMMA?
Yeah, or are you testing these glues in other plastics?
No, this is mainly, I've seen that was what it was causing the haziness were some solvent, and it was due to consolidation, etc. What we are doing now, we are testing a range of adhesive that should not cause this sort of damage. Let's say that we are excluding what is actually damaging the PMMA during bonding. So we test several adhesive, conservation adhesive, and this is a publication upcoming on the ICOM-CC conference that and preprints that should come sometimes soon. And after that, we are going to apply, because as you can see, the process of the research is always testing on material, on test material, mock-ups, and finally on objects. So we are hoping to finally apply the research on adhesive for PMMA on a sculpture in Milan. But due to COVID and other things, these things shift a bit. So hopefully we will do it soon. And so this is what we are basing on. And what is nice that we made a very nice chart in this ICOM-CC paper that is coming, where all the properties of the adhesive that we select as the best. So refractive index, mechanical properties. So people, based on the type of bond that they need to repair object, they can pick the adhesive that has the best properties for the restoration of the sculptural object, whatever it is made of acrylic. So.
Nice. And we have another question here from Marilene Maya. Congratulations for the presentations. The industry of plastics is developing and keep developing a lot during the times, but the degradation of these materials is current. Currently, this is a need in the point of view of ecology. How do you see the possibilities to block or interrupt or slowly this process when thinking in the preservation of cultural heritage? When working with degradable plastics.
Do you mean biodegradable plastics?
Biodegradable plastics.
We have a challenge now that plastics with all so we have this problem that the public now is so fascinated with the idea that plastics are polluting and plastics never go away, that there are now engineering solutions to make plastics that go away. And this is directly opposed to what we're trying to accomplish. And taking polyethylene and modifying it with starch. So you have something that might be labeled underneath polyethylene, but it's got starch in it, which is something for microbes to eat. That's problematic because it gets mixed into recycling streams. And so you've got now a polyethylene batch that has starch that nobody expected would be there, for example. And then there are other plastics like polycaprolactone, polylactic acid that are biodegradable. I think I have some interest in what we're trying with our extruder to start playing with this, but I don't have an answer as of now. What we seem to do is keep it dry, keep it dark, keep it cool. That sort of, don't reduce the opportunity for moisture and dust to form on the object to reduce the amount of microbes that get on the surface. But that's sort of where we are. Keep it cool, keep it dark, keep it dry. Yeah. That sound about right? Do you have other ideas? Anna?
Yes, I was thinking, unfortunately, we don't have so many, and this material on one end are new, but also not, and on the other end, let's say that for preventing conservation, I think we started, like I showed cycle, one of the phase of conservation of plastics started with preventive conservation, and it created a sort of basis, but I think there's so much to do yet. And especially also because the new material are evolving, and these bioplastic are now everywhere in museum, especially because artists or many designers as well, I think more designers than artists, they are using this as a concept of, we don't want to use plastic, we want to use something that, it's more as a less an impact on the environment. Although, for the artists specifically, they're going in museum. Designer, not because their products, they're spread everywhere. But still, I think what Odile suggested is our knowledge so far.
Yeah.
Say.
Reducing the light is probably the one I would go with. I'd try to keep it cooler, keep temperatures cooler, but reducing the light and removing the ultraviolet component of lighting, keeping objects out of direct sunlight, keeping lights dim.
The humidity, like you said as well, I think that,
yeah.
So yeah, pretty, yeah.
And how about the ethical issues when thinking long-term preservation of plastics? Is there any discussions about that, like replacements, or thinking, like this morning we had a talk about thinking in a preservation, the target was 500 years, but when you think in plastics, how does it work?
I actually wanted to include a case study on, replacement and this issue, because this is something ethically, very, struggling. I'm struggle. I started as a painting conservator, so I'm an old-fashioned conservator, and still for me, the idea of replacing something, I'm really struggling with. So that's why I'm trying to respect the original and do everything I can do to develop treatment, to try to conserve things. But there are some times, and that's what I want to show, but I thought the time was too short and there is to focus on other things. Sometimes it's really too late, so you cannot do anything. So I had an object where the polyurethane was totally powder, so you cannot consolidate anymore. And so then you have to think to replace, and then you think to properties, et cetera, et cetera. And when it's in the middle that you know they are replacing, there have been a lot of solutions I've seen in museum, like already doing replica, you know, and then store the object, you know, and hoping that, yeah, that a solution will come. And this is the case, for instance, of a lot of objects made of early plastic, acetate and nitrate. And I look at many of those over the years because I mean, we would like to develop, you know, some treatments for those totally cracking, and some are totally destroyed and they don't exist anymore, but some they're still there. And so it's a big question. I hope that we can find solution, but still sometimes the replica, it's something that there is no alternative, you know.
There's also
I think you have another session, right, Luis?
Exactly.
You have another session. Yeah,
Yes,
we have to jump off.
For your, it's really interesting subjects, and we'll have a chance to discuss more. Thank you. We're going to start the next session. Thank you.
Yeah.
Odile,
Bye,
Anna,
guys.
and Tom.
Thank you. Thank you so much.
Thank you again. Bye.
So I'm pleased to introduce the next session. Desculpem. Professora Rita Lages é a moderadora da próxima sessão. Eu passo a palavra para ela e a gente vai então agora dar continuidade.
Bem, gente, estão me escutando?
Sim.
Tá. Boa tarde, né? É um prazer muito grande estar aqui para apresentar, então, esses 5 trabalhos desses 5 pesquisadores, né? Fazer essa apresentação inicial, né?